I'm Daniel, and today I'll be talking about lithic clasts from lunar meteorites. What can they tell us about the moon? How can we understand the evolution of the lunar interior? And I've got to say, whoever made this photograph, this is probably one of the best photos I've ever seen. Just saying. So a bit about myself and a bit about how I'm used to giving presentations. This was actually when I was first introduced to give an hour-long presentation. I was surprised in a good way because most of the presentations I'd have to actually give as a grad student were fast-paced, 15 minutes, 10 minutes, 12 minutes. These are two of the conferences I've given talks at, and I had to speak very quickly. I had to present very technical information to a very technical audience. And it's kind of nice to know that I can slow down my pace a bit. I'm giving this talk. So if I talk a bit too slow and if I go over time, please let me know and I'll be happy to speed up. Before I get started, I'd like to give some acknowledgements. I'd like to thank GSOC for giving me the opportunity to speak today. I'm also very thankful to GSOC for providing me with a BEV-voked scholarship last year. It was very helpful for me doing my studies on lunar meteorites and for me being able to attend conferences and other institutions. I'm very grateful for that. Thank you. And I'd also like to thank two specific individuals, my advisor, Dr. Alex Ruzicka, and Dr. Melinda Hudson, both of whom I am very thankful for, and without either of their assistance, I wouldn't be here where I'm at today. Now, I'm also thankful to the Cascadia Meteorite Laboratory, which is the largest meteorite laboratory in the Pacific Northwest and has some very important goals for advancing meteorite research. The first is to promote meteorite research. We do this through multiple ways. One of the ways is by training undergraduate students how to classify rocks from space. So they get to be the first people to look at a space rock and understand how it formed and do the actual work and analysis. So these are two examples right here. I'd also like to acknowledge George, who's in the audience today, for doing his own meteorite research on Martian meteorites and winning a very prestigious award, the Behringer Family Fund for Meteorite Impact Research, which is given to only 5 students worldwide each year. So I'd like to give a round of applause to George. And one of the other goals of CML that I'd like to highlight is to maintain and increase the Portland State meteorite collection. Now, initially, CML started with just 1 meteorite, but throughout the years, we have over 1,500 samples and more. So one of the goals is to expand the collection to get as many samples as possible for academic research, but also at the same time for more outreach effort, trying to bring more attention to the public on raising the awareness of meteorites. Now, I'm going to sort of go a little bit off tangent here and talk about meteorites and what actually they are before, since I'm giving a talk on lunar meteorites, I should probably talk a bit about meteorites first. So just a bit of terminology right here. So initially we get meteorites from, just put the laser pointer on, we start with an asteroid in the asteroid belt, or sometimes a comet, and it gets hit by a collision, parts of it break off. We call these objects meteoroids. And they travel through space until they enter the Earth's atmosphere. While they're in the Earth's atmosphere, they burn up or ablate, so they melt. We call that light phenomenon a meteor. And eventually, if they manage to make it to the ground and land successfully, we call these meteorites. Now, a meteorite has different definitions depending on who you ask. The simplest terms are rocks from space that land on Earth. But the real term is a rock on the surface of a planetary body derived from a different body. So we actually find meteorites on the moon, we find meteorites on Mars, and we find meteorites on other asteroid bodies. So for this definition, I'm just going to refer to meteorites that land on Earth from other places, but you can get meteorites anywhere. And they can range from 1 gram to over 60,000 kilograms. And we divide meteorites to 2 types depending on how they're recovered. The first are falls. So when people actually observe the fireball moving through the atmosphere, and then they see the object, and they pick it up, that's called a fall. Or most of the times, in most cases, people just find a meteorite somewhere and they collect it. Now, the most obvious sign for identifying meteorites are what we call a fusion crust or an ablation crust. This is just a melted or glassy outer portion of the meteorite that forms as the object is entering the Earth's atmosphere at tens of kilometers per second. So it's heated up, it melts, And as it melts, it eventually cools very quickly in the atmosphere because it's very cold up there, and it forms this glass. And the glass is typically dark in color, usually black in color, and between 1 to 2 millimeters in thickness. But it depends on what kind of object you're melting, of course. And you also have these objects called regmaglyphs. We call these thumbprints. And these are just indentations that you can find in meteorites caused from the ablation process. So these are some of the easiest ways you can identify a meteorite in the field if you were to encounter one. So having said that, now let's actually talk about what happens when meteorites stay on Earth for a while. So sometimes meteorites, they break up in the atmosphere, and sometimes the fusion crust can break. So you can have fusion crust on some portions, but not on other portions. But oftentimes what ends up happening is that you have meteorites just sitting on Earth for tens, sometimes hundreds, sometimes thousands of years. And the original fusion crust can be altered or weathered into a different colored fusion crust. And you'll notice it's a little bit harder to identify this rock as a meteorite more than this rock. So it makes meteorite recovery a little more difficult when you've got weathered meteorites, but not impossible. So let's now go in a different direction. Well, now that I've explained it, how easy is it to find meteorites? The answer is not very easy. In fact, it's more times than not, people don't really find meteorites every day. So if we look in Oregon, we have 6 recovered meteorites so far. That's a very small number, especially when you compare it with the fact that in California, just one state nearby, we have 227 identified meteorites. And why is that? Why is it that some states, for example, Florida, which is where I'm from, 5 meteorites identified so far, yet Georgia, just up to the north, 25 meteorites? And the answer really comes down to the environment that the meteorites are recovered in. It's much easier to find meteorites in places where there's little vegetation, no trees, and very few rocks present. So for example, here in Oregon, we have lots of trees and we have a lot of basalt, which is a rock that's commonly mistaken for weathered meteorites. And so the most common places meteorites are found are in dry, arid regions like deserts. And believe it or not, the most common place meteorites are recovered in is in Antarctica, where we have teams of trained professionals who go on these US Antarctic or ANSMET missions, and their sole job is to recover meteorites to be used for study. And so every year they bring back, I think it's between 1,000 to 2,000 different rocks that are meteorites every year. So most of the statistics of the meteorites we have found are from Antarctica. But the second most common place is from the deserts of Northern Africa, so in the Saharan desert. And basically a lot of meteorite finders and hunters there are trained to see objects on the ground and can identify them as potential meteorites. So a lot of these are brought in from the secondary market through different collectors and meteorite dealers who then bring those in to the academic community. Now, finding a meteorite isn't really enough to say what it is. You really have to do an in-depth analysis of that. And this goes into an important thing I'm going to bring up here is how do you actually tell a meteorite is from the moon or Mars or anywhere? And to do this, we undergo what's called meteorite classification. So basically, you're providing enough information about a meteorite to know what kind it is, where it's from. But another aspect is what name do you give the meteorite? Because like I said, meteorites can fall anywhere. So if you were to find it, do you name it after the place it was found, or do you name it after something else? And usually we name it after a locality that is either nearby or where the meteorite was found in. So if a meteorite fell in Portland, we'd call it Portland. In order to publish the meteorite, it has to have an approved name. So this goes through this nomenclature committee that we work with, where you establish a name of the meteorite and what type of meteorite it is. And another thing you also need on top of that is what's called a type specimen. So let's say you go out in the desert and you find a, I don't know, 100-gram meteorite. Well, 20% of that, or 20 grams, whichever's less, needs to go to a scientific institution that's providing the classification service. And the reason for this is because scientists want to have a piece of every meteorite that they can do academic research on. And if you're a collector and your meteorite gets classified, eventually they're looking to either sell the meteorite or keep the meteorite. And so it adds value to their meteorite. So it's sort of a symbiotic relationship. The collectors and meteorite dealers get their meteorites almost like appraised, and the scientists get more samples to study and do research on. So this advances the field of science, but it also advances the secondary market for selling meteorites. Now, what kind of meteorite it is, I'm not going to really go in depth on all this, but the complicated answer is that we have many different groups of meteorites. And the advantage of doing classification is we can, for the most part, tell which group of meteorite the rock might fall into. And it's a multi-step process. The first step is you take the sample, you cut a piece of it off, and you prepare what's called a polished thin section. So this is a very thin sliver of the rock, about 30 microns thick. And the reason why it's that thin is so light can actually pass through it. So we undergo, the next step is to do optical microscopy. So we have transmitted light where we use this petrographic microscope to pass light through the sample, and we can use it to identify different features in the meteorite, potentially what mineral phases might be in the rock. We can use it to identify sometimes what the meteorite class might be, and anything unusual about it that we can use for when we do later analysis, which is step 3, to obtain chemical data for the individual minerals. So here at Portland State, we have this field emission scanning electron microscope that we use to classify all of our samples. And basically the instrument is very useful because it can tell you. So for example, if I look at this map right here, this is what's called a false color chemical map, where every color you see is assigned to a different element that's in the different minerals in the rock. And the combinations of the different elements give distinctive colors, which you can use as a guide to tell you what mineral phases might be there. So we can use this to tell us what minerals are in the meteorite. And then once we've done that, we can take individual spots that are about a micron in size, really tiny, by the way, and we can analyze each of these different points and find out what the chemical compositions are of these different mineral phases. And that in turn can tell us what meteorite group we're looking at. So that's really all meteorite classification is. But of course, the final step is once we've got all that information, we have to write it up and submit it for approval. And so we submit a form to the nomenclature committee of the Meteoritical Society. And basically we submit a form saying the name, what kind of meteorite it is, all the analysis we did on it, and whoever owns the rock and how much of the material there is. And once it's approved, it's called an official meteorite. The key thing is that when it's deemed an approved official meteorite, such as this name right here, Northwest Africa 14261, it can now be used in scientific publications, which is important for advancing meteorite science. So the whole goal is to get as many meteorites into this database as possible to have more samples to use for academic research. So I just said why it was important, but let me just rephrase it again, that the importance of classification is that it leads to new research. And what you're seeing right here are 4 different lunar meteorites that so far have been very helpful to me during my 2 years in my PhD program. So I've been able to write a couple abstracts with my advisors on some of these lunar meteorites, and some of them, which I'll show in later slides, are very unusual compared to most lunar meteorites. And all of this was done from different meteorite collectors who have sent in samples to get classified and to be used for scientific research. So that's the importance of classification. And now that we've gone through that, let's actually talk about lunar meteorites. But before I get there, we have to talk about the moon. And the first thing is, well, okay, we have a moon. How did it form? So pretty much think back 4.5 billion years ago when the Earth was just starting to form. And the Earth was struck by a Mars-sized object called Theia. And so in this resulting collision between the two bodies, you formed this large disk of debris that orbited the Earth's gravitational field. And eventually this debris all came together and coalesced and formed the moon that we see today. So once the moon formed, the energy required to put together all those fragments led to a lot of thermal energy being released, and the moon actually melted, and you started off with a molten moon. We call this what's called a lunar magma ocean, or LMO. And so the main idea for how the moon sort of chemically evolved once it was molten was called the lunar magma ocean model. And the way it works is initially your moon is pretty much molten, and then eventually you first form the core of the moon. So this is called differentiation. So like on Earth, we have a crust, mantle, and core. The same thing exists on the moon. So you first form your core, and then you start forming your mantle. And as you're forming your mantle, you start to crystallize this mineral called olivine. And then after you crystallize enough olivine, all of a sudden, another mineral becomes stable in this melt mix called pyroxene. And so now you're crystallizing olivine and pyroxene, and these make up what are called your mantle cumulates. So your mantle of the moon is made up of these two elements, these two minerals specifically. Then after about 80% of this magma ocean has crystallized, all of a sudden another mineral becomes stable. That's plagioclase feldspar. Now, plagioclase feldspar is one of the most common minerals we find on Earth, and it's one of the most common minerals we find on the moon. In fact, when you form plagioclase feldspar, it's actually less dense than the surrounding melt it's in. And like ice that you put in water, what does it do? It floats. So this plagioclase feldspar floats to the top and forms this thick crust, which we call an anorthosite crust. Anorthosite is just a rock that's made up almost entirely of plagioclase feldspar. And so you form this thick anorthosite crust. And then at the very end, when you've got maybe, I don't know, 1–2% left in this magma ocean, all of your what we call incompatible elements, these are just elements that prefer to stay in the melt over crystallizing into these different minerals, they have to crystallize somewhere. And so they turn into this layer, which is called UR creep. Interesting name. I'll explain what the creep stands for on the next slide. Or you form what are called the IBC, or the ilmenite bearing cumulates. So this is the final dregs of this magma ocean that crystallizes. And so now you're left with a fully crystallized moon, fully solid. And now let me explain the formation of the lunar high magnesium suite, or MG suite. So you've crystallized your whole moon, but all of a sudden that UR creep / IBC layer, those minerals in that layer are actually much more dense than the minerals that are below it. And so just like if you had a lava lamp, you undergo what's called a Rayleigh-Taylor instability, which means if you have a more dense liquid over a less dense liquid, it basically displaces the less dense liquid upwards as it gravitationally sinks, and you get mixing of the lunar mantle. We call this cumulate mantle overturn. So your initial stratigraphy you had all of a sudden gets mixed. And so now you're bringing all these early formed olivine and pyroxenes that were initially here, you're now all of a sudden bringing them to the surface. And what does that do? Well, initially, like I said, they're stable here, but they're not stable here. So they melt. They undergo what's called adiabatic decompression melting. And when they melt, they form these, what we call plutonic intrusions, which are just these, think of these magma chambers inside of the crust of the moon. And these crystallize to give us what we call the MG suite rocks of the moon, or the MG suite. So an example would be this Apollo 7 troctolite, which is a rock made up of olivine and plagioclase feldspar that formed in one of these magma chambers. Okay, so we've talked a bit about the different kinds of rocks you could find on the moon. We talked about the formation of the MG suite. Let's actually talk about how we knew all this. And we knew all this because back in 1969, we initially had Apollo 11 land on the moon and bring back our first samples of the moon. And since then, we had Apollo 12, 14, 15, 16, 17. And we also had 3 unmanned missions from the Luna 16, 20, and 24 rovers that brought back samples from the moon. And just recently, we had the Chang'e 5, which brought back another sample from the lunar surface. And we've had a few other ones too. Now, initially, if we look at the moon today, you'll note that we have, of course, a near side and we have a far side. And all of these recovery missions took place on the near side, and we don't really have anything on the far side. Now, when we look at the moon, also, we'll notice that we see almost 2 different shades of gray. We have this light gray material, which is called the feldspathic highlands terrain, or FHT for short. This is basically enriched in your anorthosites, or the plagioclase feldspar rich crust that I showed earlier in that model. And so when the Apollo astronauts brought back samples from these regions, we had something called ferroanorthosites. These are essentially the anorthosites that made up that crust. We also sampled these darker areas. These are called the lunar maria regions. And Apollo astronauts brought back what are called mare basalts. So these are essentially, almost think of them as like lava floodplains where you had lava that just covered the surface of the moon and led to this darker color that you see here and crystallized to form these basalts. So you'll notice, again, like I said earlier, all of the return missions sampled the near side of the moon, but nothing really on the far side. And initially, when the samples were brought back, people made the LMO model for how you form the moon and evolve it over time. And it wasn't until about maybe 20 or so years later when, oh, I forgot to mention, these are where your MG suite samples were sampled. So this troctolite was sampled from Apollo 17. But anyways, the idea was that 20 years later, people looked at the samples and realized they were recovered from a very narrow region of the moon that happened to unfortunately sample an anomalous, geochemically anomalous region of the moon called the Procellarum creep terrain. That's where the creep comes from potassium, which is abbreviated K, your REEs are your rare earth elements, and phosphorus, which is abbreviated P. And so basically it turns out that when you look at the chemical compositions of most of the samples brought back from the Apollo missions, they're unfortunately contaminated from material from this area. And that, of course, begs the question, well, it would be great to sample material from this part of the moon, the far side, and mostly from the feldspathic highlands terrain that is far away from this anomalous region on the moon. And you might be wondering, well, how do we know that how did we obtain this information to say that this was anomalous? Well, we have orbiting spacecraft around the moon that have different arrays of detectors. For example, this particular element, thorium, was detected using what's called a gamma ray spectrometer. And so it basically picks up the X-rays and it can give you a rough estimate of the global concentration of this element. So those are very helpful in telling us where different parts of the moon are for sampling. And so in the absence of future sampling efforts until Artemis returns in 2025, what can we use instead to give us a better sampling of the lunar far side? And the answer is lunar meteorites. So lunar meteorites, as the name suggests, since I talked about meteorites, these are rocks ejected by impacts on the moon. So the moon, of course, as we know, is very heavily cratered. It's got craters on both the near side and far side. And whenever an object hits the moon, it ejects more material. And if that ejection velocity of that material exceeds the escape velocity of keeping stuff on the moon, it eventually enters an Earth-crossing orbit, hopefully, and it lands on Earth. And we can sample those as lunar meteorites. Now, what are some advantages of using lunar meteorites? Well, there's two main advantages. The first thing is that they can be derived from anywhere. Like I said, the moon is heavily cratered on both sides. So any of those craters on the moon, especially the larger ones that form these big basins, can provide material that can land on Earth. But the second most important thing is that they can contain material that are mixed from different areas of the moon. So just think about this. You have a crater that you form on the moon, so you eject some material out. And then you have a second crater nearby that ejects other material out, but it also ejects the previous material that was ejected. And so you end up getting this layering process. And so eventually you can form what's called the lunar regolith, which is just the outer covering or surface of the moon. Maybe think about a few meters to 20 meters deep of just ejected material from many areas that gets mixed together. And so basically, if you were to have one more ejection, one more crater forming event, and you eject all that material together and you sample it in this lunar meteorite, well, you can have parts of this lunar meteorite that maybe come from the far side, and you can have parts of it that come from the near side. So the advantage of lunar meteorites are that they provide us a much better random and representative sampling of the lunar surface than the Apollo and Luna samples so far. And if you pay close attention, these objects right here are going to be the focus of my talk. These are called lithic clasts. What that means is that they're just rocks in rocks. Think of them as like on Earth, we have conglomerates and breccias. You just mix a lot of different fragments together. That's basically what happened on the moon. So now that I've given a lot of background information, let me actually pose some research questions. So I talked about the advantage of using lunar meteorites, but now let's talk about some disadvantages. Well, whenever you have impacts that strike the moon and eject material, these high energy collisions create shock waves. And these shock waves propagate and they create compression waves. They basically move through the material and they can basically deform the material. And that's a problem because whenever you have these secondary shock effects, you have what's called shock metamorphism. And basically this chart right here is comparing the temperature versus pressure. And this is showing for example, on Earth, we have regional metamorphism. So for example, when we have our typical metamorphic rocks, they've experienced pressures in this range and temperatures in this range. Well, on the moon, when you have shock metamorphism, the energy from those collisions are lead to pressures much higher than that you see in the inside of the Earth. And therefore, you can generate much higher pressures. And when you do that, because you're compressing an object, you can actually generate temperatures much higher as well. And so the whole point of shock metamorphism is that because of these high energy impacts, you're creating shock waves, they propagate through material, and they lead to these high pressure, high temperature, secondary effects that alter and basically change the original rock or whatever material they're moving through. And this is a problem. And I'm going to show you this diagram right here. This is basically, so what you're seeing here is a schematic of a crater. So here would be the center of the crater, and then this would be as you're going towards the rim of the crater. So the idea is that as the object strikes and you have your shock wave that's pretty much moving throughout all the material in all directions, basically your shock pressures closest to the center would be high enough. So this is in gigapascals. So 60 to 500 gigapascals, basically you would get pretty much melting. So whatever is there would be completely melted, almost vaporized. Probably some of it was vaporized, turned directly into a gas, but most of it would be totally melted. So you'd have these giant melt sheets in that region. And then as you move further away from that crater, you would have some rocks that fall into region B, which undergo what's called solid state deformation. So maybe they haven't melted, but they've been what's called plastically deformed. So if you want to think about plastic deformation, think about if you took a copper wire and you bent it. That's generally what plastic deformation is. It's irreversible damage that doesn't go back to its original orientation. And if you look at region C, where you're in probably the 5 to 10 gigapascals range in pressure, these rocks undergo mechanical deformation or fracture. So they just break. We form these fractures and the rocks break. So these secondary shock effects are present in a lot of lunar meteorites because they had to have been excavated by impacts. And ideally, you'd want to be able to disentangle these effects and say, okay, if I look at this lunar meteorite, some of these clasts might have been heavily affected by these shock effects. Maybe some of these haven't. Maybe some of these came far away from the crater, and when they were ejected, they weren't able to be that deformed from those shock waves. And so a part of my research is how can you disentangle lithic clasts from lunar meteorites for some that have been extremely shocked and some that maybe haven't, and they can tell us potentially more information about their original formation process from that lunar magma ocean model that I showed earlier. Maybe they can give us more insight into that model than clasts that are extremely shocked. So my two questions for my research are, question one, what role did impacts actually have in physically and chemically modifying lunar materials we find as these lithic clasts in lunar meteorites? How have they been altered, and what were they like before they were altered? And two, if we can disentangle the more altered from the least altered lithic clasts and find some that are what we call pristine or unaltered, what was the origin of those materials? What can they tell us about the original lunar magma ocean model that I showed earlier? Do they support the model? Do they agree with the Apollo samples? Or maybe because they were recovered from a different region, maybe they can provide more information and tell us that we have to go back and revisit our lunar magma ocean model and maybe add some changes to it. Or maybe the model altogether is incorrect. So it's important first that we can identify shocked versus unshocked lithic clasts before we go forward and talk about the lunar magma ocean. So that goes right into my objectives. Objective number one is to quantify how much shock processing we have within these lithic clasts. So we're going to look at, basically I'm looking at a whole bunch of different lunar meteorites, some that are what we call anorthosites, rich in feldspar, some that are troctolites, rich in olivine and feldspar, and some lunar meteorites that are different altogether. And can we look at all of those lunar meteorites using what we call a combined chemical crystallographic technique, where we can basically create this shock transformation index and say, okay, let's filter out from this lunar meteorite clasts that are heavily deformed and clasts that are pristine or unaltered, and then focus our attention on those unaltered clasts and use those for interpreting models for how the lunar magma ocean might have formed. And so from this study, we have 4 samples so far that we're planning on doing this from. We have results from the first 2. I'll be discussing that today. And we're currently in progress on 2 other samples. So the 2 samples I'll be talking about is Northwest Africa 13531. That's this sample right here. And Northwest Africa 14900, which is this sample right here. And you can see they're a bit different in their texture. They appear different. Now, how are we going to do this? How does a chemical crystallographic technique even work anyways, right? So to do this, we involve the scanning electron microscope at Portland State University. And I'm going to spend a few minutes talking about how this all works. So this is our SEM right here we have on campus. If you were to look inside the chamber where we put the sample, you'd see the sample goes right here. And we have all these different detectors pretty much aimed at the sample trying to collect some kind of analysis. So we have what's called our column right here. So this is the inside of the SEM. This is what this part is right here. And it's all started with this electron source. So you generate electrons, they're accelerated down this column, and they hit your sample. Once they hit the sample, one of three things can happen. The first thing that can happen is that these electrons can interact with atoms in your sample. And because different atoms in your sample, for example, could be different elements, which means they could have different sized nucleus. Basically, these electrons can interact with those nuclei differently, and some of them could be what we call elastically scattered or backscattered. So they can interact and go back up, where they're picked up by this detector right here. And these formed the basis of what we call backscattered electron images. Now, the key thing to note about these backscattered electron images are that they're heavily controlled by this process that I showed right here. And this process is dependent on the size of the nucleus. So big atoms from elements like iron are going to have much bigger nucleus sizes than elements like silicon or elements like sodium. And so because of that, you're actually going to get more electrons that are easier to be scattered upwards. And therefore, whenever you're looking at a backscattered electron image, we call this a Z contrast, or basically an average atomic number image, because electrons that come from larger nuclei that intersect can provide more signal, and thus they appear brighter in these images. And then those that don't appear darker. I'll explain a bit more on that. Now, the second thing that electrons can do when they interact with their sample is they can form characteristic X-rays. So how this works is the electron comes from the source, it hits the sample, it knocks off another electron from these atoms of your sample. And when it does that, you release this X-ray. Now, depending again on what elements you're looking at, those atoms can release different types of X-rays with different energy levels. And so we call these characteristic X-rays. So basically, the whole point of this is that you can use these to tell you what sort of elements you're looking at. And you can use this to tell you what mineral phase you're looking at and what its chemical composition is. So the two work in unison by using backscattered electron images combined with EDS, or energy dispersive X-ray spectrometry false color maps. And the third interaction you can get is if electrons hit your sample, depending on the orientation of the crystals in your sample, they can interact with what we call mineral lattice planes, which are just an arrangement of atoms in a certain plane. They can interact with that and form these what we call diffraction patterns, which we use for the basis of EBSD, or electron backscatter diffraction. The importance of this is EBSD can tell us what mineral phase we're looking at, it can identify that, but it can also identify the orientation of that mineral. So we can get information into its crystallographic structure, something we can't really do with the previous two methods. So if we combine all three methods together, we can get the chemical information from the EDS detector, and we can get the crystallographic information from the EBSD detector. So using all three together can tell us a lot about the lithic clasts we're looking at. So now let's actually talk about some of the results from our samples. So let me go on, I'm going to go in this in a bit of detail here. So the first sample we're looking at is Northwest Africa 13531. It's what's called a lunar melt breccia. What that means is that you have all these lithic clasts that are inside of this matrix that was melted and crystallized. So you have lithic clasts in a crystallized melt matrix. And so what we've done here is we've identified 6 lithic classes of interests. We've labeled them. And what you're seeing here on these images right here, these are false colored EDS chemical maps of each of those lithic clasts. And so, like I said earlier, every color is mapped to a certain element. And when you combine the colors, you get a certain color pattern for a specific mineral. And so what I've done here is I've actually labeled what the color, what mineral the labels correspond to. And you'll notice right away, each of these clasts are all almost purple, which means that they're very rich in plagioclase feldspar. In fact, most of these lithic clasts are what we call anorthositic clasts. They're basically all plagioclase feldspar. You'll notice this first one right here has a little bit of olivine, and it's got a little bit of pyroxene right here as well. And it's a bit hard to see, but if you look close at some of these clasts, you'll notice that you see all these little tiny cracks right here. These are fractures. And so a lot of these clasts are heavily fractured. likely from the impact process that deformed them. But you'll also notice if you look closely, some of this plagioclase feldspar right here looks a little different than some of this plagioclase feldspar here. And that's because it texturally is different, it's smooth. Whereas here, you actually see coarse grains. And also in some of these clasts, if I go right here, you'll find what's called impact melt glass, which is just if you were to melt those minerals and then that crystallizes as a glass. That's what we call impact melt glass. So that's what EDS and SEM can provide us. But what about if we add EBSD in? So now let's actually add in the crystallographic information. But before I get to that, let me actually talk a bit about the chemical results from these clasts, because it's important that we actually talk about their chemistry. So this chart right here that you're looking at, it seems a little complicated, and it actually is. It took me a while to understand it at first. But basically, this is comparing the ratios of certain elements in one mineral against certain elements in another mineral. And the reason this is important is because the different rocks brought back from the moon, the magnesian suite, the ferroan anorthosites, they have different chemistry. And so basically right here, this outline represents the chemical compositions of your Apollo ferroan anorthosites. And in case you forgot, ferroan anorthosites are, again, the global anorthosite flotation crust that formed during that initial LMO, lunar magma ocean, differentiation process. So this crust right here, samples from here are your ferroan anorthosites. So this is where they plot chemically. Now for the magnesian suite rocks, remember again, these are essentially plutonic rocks that formed by your mixing of the lunar mantle ocean, the mixing of the lunar mantle from your ilmenite-bearing cumulates that sank. You form these plutons that crystallize, and rocks from their MG suite. And that's where they plot right here. So when you look at our lithic clast, you'll say, okay, some of them plot in the field for MG suite rocks. Some of them plot in the field for ferroan anorthosite rocks. So we have a pretty good sampling so far of the different anorthosites brought back from the Apollo missions, which is good. In one lunar meteorite, we can sample 2 different kinds of rocks. But then we have this one clast right here, clast 1b. And it doesn't fall into either of these 2 categories. So what's going on there? Is this a unsampled anorthosite that hasn't been sampled by the Apollo samples and we're just now sampling it? Or was this initially in one of these 2 fields and maybe it was melted or altered by shock deformation and then its chemical composition changed and it just moved over here? That would be something of interest to know, because that would mean if we're looking at lithic clasts and lunar meteorites, do we need to be careful about what their chemical compositions tell us? Maybe they don't plot in where they should be, and maybe they've been altered chemically. And so for this, we focused on clast 1b, which is right here. So this is sort of what I showed earlier. Again, very rich in plagioclase feldspar. But now let's throw on the extra lens of EBSD. And I'll just leave this up here for a second. So the cool part of EBSD is, again, you can identify what the minerals are, and you can identify how they're crystallographically oriented. So you'll notice that there are 3 colors primarily on this EBSD map. You'll notice there's a lot of purple. So the purple color means it's plagioclase feldspar. These parts of the sample have been identified as plagioclase. The orange parts have been identified as pyroxene, and the green parts have been identified as olivine. And when I zoom in on that clast 1b, let's see, it's right here, you'll notice that it's very purple, which is what we sort of knew earlier. It's rich in plagioclase feldspar. But you'll also notice I have these areas in here, these like bands. They're sort of dark in color. There's really no color there. We call these amorphous bands. And these formed from the shock deformation process that altered clast 1b initially. So remember those regions I told you where the plagioclase was glassy and smooth and not coarse and crystalline? Well, this plagioclase has been transformed to an amorphous glass, which we call maskelinite. And because maskelinite is a glass, it doesn't really have a mineral crystal structure. And so the EBSD detector can't index it as a mineral, and therefore it leaves it blank. And so all these bands running through here are just amorphous maskelinite, which we couldn't see earlier from the EDS map. So EBSD gives us that next level perspective where we can say we have evidence of deformation in the clast where plagioclase has been shocked to form maskelinite. And through experimental work that's been done in laboratories trying to find out what kind of pressures can form maskelinite, were probably at least 22 gigapascals, which for reference, that is very high in pressure. And so what that means is that this class has seen deformation, and this raises the question, has this deformation led to that difference we saw in its chemical composition from the two anorthosite groups? And another way we can check to see how deformed the clast is using what's called a misorientation map. So this map is a little trickier to understand. This is called an EBSD grain orientation spread, or GOS map for short. And what you'll notice are that there's a whole bunch of colors. You'll see a lot of blues, some greens, some oranges, and some yellows. And the way you really want to interpret this map is that the bluer the color, so all these blues indicate regions of relatively low deformation, whereas regions that have greens, yellows, and oranges are regions with relatively higher amounts of deformation. So a few things you'll notice right here. You'll see that the regions that are outlined as greens and yellows, these tend to fall where these lithic clasts are. So for example, clast 1A, which is sort of right here. We have clast 2A, which is right here, and then our clast 1B, which is right here. So we found that on average, these lithic clasts tend to be more deformed than the surrounding matrix that they're in. And when we look closely at lithic clast 1B, we also find that within the clast itself, deformation is heterogeneous. On some parts of the clast, they're more deformed than other parts of the clast. And so we can say that this clast must have seen at least two distinct shock deformation events during its lifetime. The first led to the deformation in the clast. So wherever it was initially on the surface of the moon, an impact struck, broke off a piece to form this clast and deformed it. And that clast landed somewhere on the lunar surface where it incorporated with a bunch of other clasts to form this meteorite. Then once you formed the meteorite, you had a secondary shock event, a secondary impact, which deformed that whole rock altogether, created the amorphous bands. And then you finally had the final impact event, which excavated it and got it in Earth crossing orbit. So using EBSD with SEM and EDS together, we can get this chemical crystallographic information we need to basically identify that this class has been heavily deformed and seen two distinct shock events. So that's from our first sample. And this is from the second sample that we've looked at so far. So this is Northwest Africa 14900. And you'll notice it has so again, what you're seeing is a false color chemical map of the entire meteorite. Again, every element is mapped to a certain color. So anything rich in magnesium is going to be green. Anything rich in calcium is going to be red, iron, blue, etc. And you'll notice that the texture of this rock is different from the previous rock. That's because instead of the matrix being melted, this matrix is just made up of smaller, tinier fragments of rocks. Think about if you took like a conglomerate and you have all these little sand grains that are holding these larger pebble-sized objects. That's sort of what a fragmental breccia is. But I want to draw your attention here to this one clast right here. This is the largest clast in this meteorite, and it's all green. That's because it's dominated by this one mineral, olivine, and it is called a Dunite. Now, what are lunar Dunites? I have to go a bit more back into explaining what they are, but basically they're olivine-rich igneous rocks. So basically almost entirely comprised of just one mineral, olivine. How do they form? Well, from experimental modeling, looking at the LMO model, essentially these early formed mantocumulates that I talked about, made up of olivine, are pretty much your lunar Dunites for the most part. And if you look at some remote sensing work, which are just orbiting spacecraft using different methods to identify certain features on the moon, it's been found that on the surface of the moon, there are likely olivine-rich mantle rocks that are likely exposed following these large basin-forming impacts that exposed parts of the lunar mantle and ejected material everywhere. And so what you're seeing here is an image showing crustal thickness on this axis. And basically on areas we have relatively thin crust, that means that the mantle is basically right there. That means that you had large basin forming impacts that excavated all these Dunites onto the surface. And that's likely what these star-rich areas are right here. So we know for a fact that we have some areas on the moon that probably come from the lunar mantle, but we haven't really sampled those regions yet. And well, maybe we've collected them somehow. Maybe they're somehow in our previous Apollo and Luna collections or in lunar meteorites. And the answer is not really. We haven't exactly sampled the Dunite classes that we're looking for. Most of the Dunite clasts that we found, for example, this cataclastic Dunite, which was found from Apollo 17, was suggested to be related to MG suite samples. So again, related to the MG suite, not to our mantle cumulates. So this raises the question, how can we identify lunar Dunites that are actually from the mantle? And if we can, what can they tell us about this LMO process? Because again, the whole point of identifying material from the moon is to get a better sense of explaining the models for how you form the moon and evolve it through time. And the more samples we get, the better constraints we can place on that model. So let's look at our Dunite clast. So this is, of course, our false color chemical map. You'll notice it's all green. That's because it's all olivine and it's very magnesium rich. So this is just the chemical composition of this class. I won't go too in detail about that, but the whole point is it's all olivine and it's got a little bit of this other mineral right here, which is called chromite. Now, chromite is going to be this pink mineral right here. And it's important that we have different minerals inside of a class, because if you just have one mineral and you're trying to get information out of it, it's very difficult. But when you have multiple minerals inside of a rock, they can provide more information into maybe how the rock formed. So this is a little bit complicated. This is called an olivine spinel geothermometer. And one thing we can try to get out of this is what we call an equilibration temperature. What that means is at what depth did the rock potentially form at, or could have formed at? So plugging in a lot of chemical data into this very tedious equation that took me a few hours to understand, we can obtain an average equilibration temperature for this Dunite class of 994 plus or minus 30 degrees Celsius. So what does that mean? Just a number, right? Well, the number can mean one of two things. The first is that this represents the temperature of when that Dunite class crystallized from a melt. And if we know the temperature of when it crystallized from a melt, and we know what's called the lunar selenothem, which is sort of similar to a lunar geotherm, which is basically where you say, as I go down in depth into the interior of the Earth or the moon, temperature goes up in this specific way, and you can determine what depth you're roughly at, depending on what temperature the rock formed at. So that's what it could tell us. That would be magmatic temperature. But the other thing it unfortunately could tell us is what's called a subsolidus reequilibration temperature. What that means is that the initial temperature that the rock formed at had been changed or chemically, and so the temperature it gives isn't accurate to the actual magmatic temperature, which gives a different temperature altogether. So plugging in these very detailed chemical information from the olivine in the clast and from the chromite grains in the clast, which we needed both minerals to do that, what we found was that this Dunite class, which is this point right here, is off of what's called an equilibration line. So what that means is if I form this Dunite and I form the olivine and the chromite, and they were in equilibrium, which means they formed at the same time, the chemical composition of that chromite compared to that of the olivine would have to follow this line. If there were any changes to that equilibrium, which can happen if the rock was, for example, slowly cooling at depth, it would move off of this line. And in summary, because it's off of the line, that tells us that this temperature is not the true magmatic temperature, and we have to correct for that. And when we do correct for that, we obtain a temperature of about 1225 degrees Celsius, which is in range for forming Dunites from either the MG suite way or forming them from mantle cumulates. So that's good. So we know from this temperature, one of those two hypotheses is true, but which one? Because that's what we're trying to find. So why don't we compare this Dunite with other Dunites from other samples that were found? So this is looking at another Dunite class from another lunar meteorite, NWA 11421, that was studied back in 2019. And basically, if we were to compare all of these different chemical and textural statistics together, we'll find that they're pretty similar. And the authors of this paper implied that this Dunite class, because it had other minerals in it, they were able to derive a pressure that it must have formed at. And their pressure was estimated to be about 68 kilometers in depth, roughly, that this class formed at, which is in the lunar mantle. So they said that their Dunite class formed from the lunar mantle. And when we compare all of our data, or equilibration temperature, or olivine and chromite compositions with their data, we get about a similar result. We also can compare the chemical compositions of our Dunite with the MG suite Dunites that have been found so far and see, are they similar, are they different? And I don't want to talk too much about this, but the main summary from here is that the compositions of the olivine and the chromite in our Dunite clasts are similar to the MG suite troctolites and Dunites. So that'd be these blue points right here and our triangles here, but they're not exactly the same. And the other thing that I want to talk about is, in this figure right here, there was modeling done to try to give constraints on what the composition of Dunites that formed in this magma ocean, what composition they would have. And our sample was here, and those cumulates would be here from the LMO. So our sample doesn't plot with those, but they plot with MG suite samples. So we sort of have some mixed signals here in summary as to how you form this Dunite clast. We know that it is one of the most primitive Dunites that's been sampled thus far from its chemical composition, but we don't know if it's an actual cumulate that formed in that lunar magma ocean from the mantle of the moon, or we also don't really know very well if it could just be an MG suite sample and not related to any of the mantle cumulates. So also, could it have been impact modified? Because like I was talking about earlier, EBSD can provide us that useful information. Has this class been altered where its chemical composition has changed? And therefore, maybe the information I got earlier was sort of misleading to which of these two processes it might have been from. So, of course, it would be useful to do EBSD of the olivine in this Dunite class. And we did. So pretty much what you're looking at here is a EBSD mineral phase map. So you'll notice it's all green because the phase that was indexed was olivine, but you'll notice this pink right here, that's our chromite. But one other thing you'll notice here that you can't see on this image, you notice all these grain boundaries around these olivine grains. So this isn't just one olivine grain. This is actually many olivine grains that are basically stuck together to form this Dunite clast. And a better way to see it is actually this map right here. So besides having a lot of pretty colors on it, this map is called an EBSD inverse pole figure IPF map. What that means is that if you remember what I told you about EBSD being able to tell you what mineral phase you're looking at, but it can also tell you the orientation of the mineral crystallographically in that rock, what you'll find is that on the inside of this Dunite class, all of these olivine grains right here are blue. That means that they're all crystallographically oriented the same direction. Whereas on the outside, on this side, and on this side, they're all different colors. So what that means is that we have this core and we have this rim, and there's some genetic linkage between the two. But what that likely means is that there was some process that disturbed this grain to have moved the outer parts of it in a different orientation relative to the center. So it's been deformed to some extent, but how much? And that's where we can go back to our Gauss map, which I showed on the previous sample, where anything that's blue is relatively not that much deformed, whereas anything that's green, yellow, and trending into orange is more deformed. And you'll notice here, this is basically all greens, some yellows, and some oranges. So it's been, for the most part, heavily deformed. So what can we say about this Dunite class? Well, it's been heavily deformed. It's been altered from at least 3 shock events we've estimated, maybe 2. We're sort of debating that right now. But the first event had to have initially fragmented whatever material you hit, whether you hit this MG suite pluton or whether you have mantle material that was excavated and then you hit it with another impactor. You had to have fragmented that material somehow. And you had to have what we call sintered it, which means that you basically, it's almost like you fuse parts of it together. So you had this core and you had this rim, they sort of fused together, but they were at different orientations. So you formed the clast. Then the second event deformed the entire clast uniformly because we have green everywhere, not just isolated in the core of the rim. And then you had to have excavated it on the lunar surface, incorporated it into the lunar meteorite with all the other clasts. And then you had to have had a final deformation event, which deformed just the outermost edges of the clast. And I didn't explain this very well, but on the previous slides, if you look very close on the edges of the clast, you'll see some blue areas, just on the edges. And that area has experienced a third deformation event. So these are the 3 events that this one class in this one lunar meteorite experienced. And we can get all this information just from EBSD and from chemical analysis. So as my advisor once quoted, that's it and that's all. And for that, I say thank you, and I'll be happy to answer any questions.
And remember to repeat the questions. Okay.
Yes.
I have two questions. One, I didn't understand the ablation process and how it caused thumbprints.
Mhm.
The other one, what's the difference between a primitive meteorite and a non-primitive meteorite?
Those are great questions. So let me go back. Okay, so let's talk about the regmaglyphs. Okay, so the main idea is that when the object is entering the Earth's atmosphere and it heats up, it begins to melt or ablate. And the regmaglyphs themselves are parts of the sample that have been ablated. So you pretty much, you melt material and you form this void. And then if it cools fast enough and turns into a glass, you don't have time to replace whatever was lost. So you're just left with this cavity. So that's what, sort of like, just like a cavity left behind from losing material that wasn't able to get replaced in time, and then it just solidifies. So you lock in that texture at that moment that after the material was lost. And your second question was?
What's the difference between, you mentioned the primitive meteorite, but I don't understand the difference. What is a primitive meteorite and how does that vary from a non-primitive meteorite?
So what's the difference between a primitive meteorite and a non-primitive meteorite? Okay, so this goes into this complicated chart, but the main idea are that primitive meteorites, we call them undifferentiated. The main thing is that whatever parent asteroid these objects came from didn't experience a large amount of melting or didn't melt. So when I showed the moon and I showed how it started from this large ocean of magma, these asteroids didn't experience any melting at all. These just formed from objects that accreted together and gave us these asteroids. Whereas the differentiated meteorites come from asteroids that have experienced large amounts of melting. So chemically, they're different. Yes.
My question isn't so profound, but this tells what's happened in the past. What's useful? What's the information used for?
So the whole idea behind why we're doing all this is if we can understand shock deformation histories of lunar meteorites, and we can say that some lunar meteorites have been more deformed, some have been less deformed. If we're going to be doing scientific analysis and taking parts of these meteorites and crushing them up and putting them in these instruments called ICP-MSs, what they basically do is they can give you ages or specific compositions for certain lunar meteorites, and people plug those into models for the LMO. The important thing is you don't want to be focusing on lunar meteorites that have seen lots of shock deformation, because if you do, they could have been chemically altered, and so the results you get might not be true to what the lunar meteorite actually was before it was altered.
But even more simple, why? I mean, I don't know, that's what I'm struggling with. Is it going to help what if we land on Mars? I mean, is it that kind of analysis that's going to help with this bigger picture?
So on the bigger picture scale, what this can tell you is we can understand what the effects that asteroid impacts have on the surfaces of planetary bodies. So not just the moon, but on Mars as well. Mars has seen some large forming craters. Asteroids that we've sampled have been hit by other objects.
Okay.
So we can apply this on a larger picture for just understanding how objects have been altered or affected by collisions.
Okay.
Yes.
I think I missed how you identify a meteorite just having come from the moon.
That's a great question.
And repeat it.
So the question was, how can we identify that meteorites are from the moon? And I'm going to go back sort of to the very end here. Okay, so one of the things we can use is this plot right here. So what we use in this plot is we're looking at the ratios of certain elements in the different mineral phases. And we can use them if we look at, let's say, a lunar meteorite that has, I don't know, maybe like lots of clasts. And we take the composition of each of those clasts, and we look at the composition of these elements in pelagic clays, plot them against the composition of these elements in olivine and pyroxene. If they plot within the fields outlined for where the Apollo samples plot, when they were, which we know were taken from the surface of the moon, then we can say with good certainty that these are likely from the moon as well. And most of the moon rocks that we see have a very different composition of plagioclase feldspar than that we find on Earth. In fact, this plagioclase feldspar recovered on the moon is very rich in calcium. On Earth, most of the plagioclase feldspar we have is what we call intermediate. So it's sort of at a value at about, if I were to just extend this plot to the left, they plot somewhere between like 30 and like 50. Here, the calcium over calcium plus sodium ratio in plagioclase from the moon is distinctly very calcium rich. And so it's going to be 85, 90, 95. And you don't really see that on Earth, except in very rare occurrences. So with good certainty, you can use that to say these are probably from the moon. Yes.
Well, since the moon presumably was at least partly knocked off a piece of the Earth, why? How did this difference in composition go?
That's a great question. So the question was, if the moon was formed from an impact on the Earth, then why do we see this difference in composition arise? And I'm just going to go back to this first image right here. Okay, so one of the main ideas is that when you sample rocks from the moon and you compare them with rocks from the Earth, those rocks from the moon are what we call relatively volatile depleted. So they're relatively depleted in certain elements like sodium, potassium. And some ideas to answer why they're depleted in those elements are that when you had this impact on the Earth and you formed this debris disk, a lot of the volatile elements have a lower melting temperature than some of the more refractory elements like calcium or, for example, thorium. And so these elements would evaporate into the vacuum of space, whereas you'd retain the more refractory elements. And so when you form the moon initially has lost some sodium and potassium relative to the Earth. And so then when you undergo this lunar magma ocean formation, this plagioclase feldspar you form didn't really have a lot of sodium or potassium to begin with. And so it's just going to be calcium rich as a result.
So there's a couple of questions from the Zoom audience. Well, 3 now. So Topher, can you hear? Do you want to unmute and ask your question to Daniel?
Sure, Daniel. Good to see you, buddy. I was wondering what percentage of the metal flakes and metal samples that we see in our lunar meteorites are actually from impactors versus originating from the lunar material?
Hi, Topher. Good to see you. That's a great question. So I can't comment too much on endogenous material from the moon, but I can comment on the exogenous metal grains found in lunar meteorites from impactors. One way those have been identified is by looking at the ratio between nickel and cobalt in those metal grains. And basically they match that with metal that's been found in chondrites. And so the idea is that if you had a chondrite impactor and you have all these metal grains that were essentially liberated from the collision and they get incorporated into these lunar meteorites and you identify them, you can basically tell that they're from chondrites, from the impactors.
Fascinating. Thank you.
And then I think you've got a question from your advisor.
Hi, Daniel. Can you hear me?
We're out of time, we're out of time.
No, this is an easy question. Okay, so my question is, you've been studying these newly classified meteorites and finding all sorts of goodies. Are there Apollo samples that might be useful to augment your research? Or is it better to just keep looking at the unclassified because we're finding so much stuff in them? Your thoughts?
Okay, so I have a few thoughts on that. The first is the ease of accessibility. First and foremost, it's easier to get access to lunar meteorites from a collector than it is to request Apollo samples from NASA. And doing analysis, especially destructive analysis where you break pieces off for all kinds of analysis is much easier on a lunar meteorite where you can take like a 10-gram slice and break it up and do whatever you want. Whereas with a Apollo sample, it's much more controlled. But in terms of what you were actually saying in terms of how they can augment the analysis, I think it would be great to actually have Apollo samples. So for example, I talked about this one sample, this cataclastic Dunite from Apollo 17 that was picked up by the Apollo astronauts. And I think this would be a great sample to also do EBSD analysis of and compare with the Dunite class that we've sampled and see how similar or different they are. Because maybe if this sample was picked up on the lunar surface, maybe it wasn't as modified by shock deformation as the one we have, maybe. And maybe it could provide useful information for understanding our Dunite class more. So yeah, it would be great to have Apollo samples.
Sounds good.
One more question from Zoom. Vince, do you want to unmute and ask it?
Hello, Daniel. Excellent talk. Can you go to that figure of that first pole figure map? I think it was for NWA 12900.
Okay, so that was, let's see. Oh, that was this inverse pole figure map.
Yeah.
This one?
Yes, this guy. Can you talk a little bit about what the coloration here means? So I see these blue colored grains in the interior and these multicolored grains in the upper and lower. Can you explain like what that means in terms of the shock event?
Okay, so the whole point of the inverse pole figure is you're looking at the crystallographic orientation of different grains, or I guess different pixels in the grains with respect to a certain direction. So what this basically means is, if you want to summarize it, it can give you a good sense as to the crystallographic orientation of different parts in this Dunite class. So all these olivine grains that are primarily blue are at roughly either the same or similar crystallographic orientation. Whereas all of these olivine grains in these rims that have different colors are at a different crystallographic orientation. Now for your second question as to how did this happen? Well, one way to think of it is that if you took, for example, there's two ideas, and I'm sort of talking with Alex a bit about this. The first idea is that, let's say you have this one giant, olivine cumulate from the mantle exposed, and an impact breaks it into 1 million pieces. And you have a larger piece and you have other smaller pieces. And that large piece, all the grains in that large piece are in the same crystallographic orientation, and all those smaller fragments are oriented at a different crystallographic orientation. And then if you were to what we call thermally / shock sinter it together, or basically you fuse it together in the solid state, you can form this IPF map, where basically you have different fragments that just come together. And because the fragments are oriented in a different crystallographic direction, that gives you the image here. That's the first idea. The second idea, which I'm still kind of trying to wrap my head around, but let's say you start with one olivine grain. And let's say the olivine grain gets hit by an impact and it gets deformed. And you have bending along certain parts of the grain, where all of a sudden parts of the grain are displaced, they're misoriented, and they're bent. They can give a difference in their crystallographic orientation from the part of the grain that wasn't bent as much. So those are two ways you can form this map. We're still obviously trying to find out which way seems plausible, but we're probably going to say both are plausible in our future work that we're doing on this.
Great, thank you.
Yes.
What kind of body is Thea?
Thea. Okay, so basically people have been trying to understand what the composition of Thea is. Oh, so the question is, what is the composition of Thea, or what kind of body is it? There are some people who say that Thea had to have been essentially similar in composition to the Earth in terms of what we call oxygen isotopes. Because if you look at the oxygen isotopic composition of the Moon and Earth, they're basically identical. And so the idea is that if Thea was some kind of different object that formed in a different part of the solar system, it would naturally inherit a different oxygen isotopic composition than the Earth. But if it formed in the same sort of nearby to the Earth, in the same system, and it picked up the same material that the Earth did when it initially formed, they would have the same composition. And so when they impacted and mixed, the Moon would have the average of the two and thus be the same. There's some other people who say Thea was a different composition in the Earth altogether, came from the outer solar system, impacted the Earth. You formed this large debris disk. Inside of the debris disk, because it was so hot, you had what's called homogenization, which means all the elements diffused and homogenized together in this debris disk. So when you form the moon, it basically had a net value the same as the Earth. And then there are some people who suggest that parts of the moon are not the same in composition with the Earth, and you can use that to infer what Thea's composition was. Basically, we don't really know very well what the composition of Thea was, but we're trying to understand.
And we have one last comment from Dr. Burns.
Yeah, I'm gonna talk to the front. First of all, Daniel, wow, what a lecture you gave. And as a professor here in the geology department, we are very, very proud of our PhD student here. First of all, he is being mentored by Alex Ruzicka and Melinda Hudson in the Cascadia Meteorite program here. And your lecture was A+.
Thank you.
Yeah, and it was, and this is the quality of work that is being done in this incredible meteorite laboratory that we have here at Portland State. And we're very, very proud of what you are doing, and Alex, Melinda, and George up there, who got one of the GSOC scholarships. And so thank you very much, number one. Number two, for those of you in the audience, I do have a few bottles of wine. And so if you would like to join me up in the geology department, I have got some great terroir differences. If you would like to sip a wee bit of wine at the end of the night. For those of you online, you guys aren't going to get to taste any. So, but we are going to do that. I'm going to turn it back over to Sheila. Daniel, thank you very much. Great job. How about a round of applause for Daniel?
One more comment I want to read from online here. Jeffrey DeVries says, fantastic talk, Daniel, very thoroughly and logically laid out and presented for the general public, aka listeners like me. Amazing the information you can glean from the lunar geologic past from small meteorological samples. Great job.
Thanks, Jeff. Really appreciate it. Thanks for attending my talk.
Okay, great. Thank you. We're done.